Frequent ballast failures in 120-volt systems can stem from several root causes. Firstly, voltage spikes are a significant concern. These spikes occur when electrical appliances are turned on or off, during power outages, or due to other electrical disturbances. These momentary increases in voltage can exceed the ballast's rated capacity, leading to damage and premature failure. Secondly, incorrect wiring can also cause ballast failure. If a ballast is wired improperly, it might receive 277 volts instead of 120 volts. This can arise from mislabeled wires, loose connections, reverse polarity, or other wiring errors. Always double-check wiring and ensure connections are secure. Thirdly, ballast sensitivity plays a role. Some high-efficiency electronic ballasts are more sensitive to voltage fluctuations. This increased sensitivity makes them more vulnerable to failing when subjected to voltage spikes or other electrical disturbances. Low-quality ballasts represent another potential cause. Poorly manufactured or even counterfeit ballasts may not adhere to safety standards. These substandard ballasts are inherently more likely to fail prematurely. It's crucial to select reputable ballast brands. To mitigate these issues, several solutions can be implemented. Firstly, surge protection is a critical measure. Installing surge protectors in the circuit supplying the ballast helps minimize the impact of voltage spikes. Surge protectors absorb excess voltage and prevent it from reaching the ballast. Secondly, proper wiring is essential. Ensure that the ballast is wired correctly. Follow the manufacturer's instructions meticulously and adhere to all local electrical codes. Verify that all connections are tight and that the polarity is correct. Thirdly, use compatible ballasts. Select ballasts specifically designed for 120-volt operation. Choose ballasts with an appropriate voltage rating that matches the electrical system. Fourthly, avoid overloading the circuit. Overloading the circuit that supplies the ballast increases the likelihood of voltage spikes and overheating. Distribute the load across multiple circuits if necessary. Fifthly, consider thermal protection. Ballasts generate heat during operation. Provide adequate ventilation around the ballast to dissipate heat. Using ballasts with thermal protection devices helps prevent overheating, which can cause premature failure. Other considerations include verifying frequency compatibility. Ensure that the ballast is compatible with the frequency of the electrical supply, which is typically 60 Hz in North America. Age of the ballast is also a factor. Older ballasts may be more susceptible to failure due to wear and tear. Consider replacing older ballasts as part of a preventive maintenance program. If ballast failures are persistent despite these measures, it is advisable to consult a qualified electrician. An electrician can inspect the electrical system thoroughly and identify any underlying issues that may be contributing to the problem. This might involve checking the voltage levels, inspecting the wiring, and testing the grounding system. Another component of this is checking the THD or total harmonic distortion. It's a measurement of the distortion of the voltage or current waveform caused by harmonic frequencies. Harmonics are multiples of the fundamental frequency such as 60 Hz and are introduced into the electrical system by nonlinear loads such as electronic ballasts, variable frequency drives, and computers. High levels of THD can cause a variety of problems, including overheating of equipment, increased energy consumption, and malfunction of sensitive electronic devices. The Institute of Electrical and Electronics Engineers Standard 519.1992 provides recommended limits for THD in electrical systems. For example, the voltage THD should be limited to 5% and the current THD should be limited to 20%. The NEC, specifically Section 220.3, addresses the requirements for calculating branch circuit, feeder, and service loads. These calculations are crucial for safety and compliance. The NEC specifies how to determine the minimum size conductors required for various types of loads, ensuring that electrical systems can handle the anticipated current without overheating or causing voltage drop. This involves determining the total amperage draw of all connected devices and selecting conductors with an appropriate ampacity rating based on NEC tables such as Table 310.15b16. For example, for lighting loads, NEC Section 220.14d provides specific requirements for calculating the load based on the type of occupancy and the area being illuminated. Section 210.19a states that branch circuit conductors shall have an ampacity not less than the maximum load to be served. This is a key requirement to prevent conductor overheating and ensure safety. Additionally, the NEC requires that voltage drop be considered in the design of electrical systems. Excessive voltage drop can cause equipment to malfunction or fail prematurely. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. Proper voltage drop calculations ensure that equipment receives the required voltage for efficient operation. When installing and maintaining electrical systems, it is also important to adhere to the NEC requirements for grounding and bonding. Effective grounding and bonding minimize the risk of electrical shock and ensure that overcurrent protective devices operate properly. NEC Article 250 provides comprehensive requirements for grounding and bonding electrical systems. It covers topics such as grounding electrode systems, equipment grounding conductors, and bonding of metal enclosures. For example, Section 250.50 requires that all grounding electrodes be bonded together to form a single grounding electrode system. This ensures that all parts of the electrical system are at the same potential, reducing the risk of electrical shock. Section 250.118 lists the types of equipment grounding conductors that are permitted by the NEC. These include wire type, cable type, and metal raceways. Section 250.134 provides requirements for connecting equipment grounding conductors to the grounding electrode system. Proper grounding and bonding are essential for electrical safety and should be carefully implemented in all electrical installations. The NEC also addresses the requirements for overcurrent protection. Overcurrent protective devices, such as circuit breakers and fuses, are designed to protect electrical systems from overloads and short circuits. NEC Article 240 provides detailed requirements for overcurrent protection. It covers topics such as the selection and installation of overcurrent protective devices, as well as the coordination of overcurrent protection systems. Section 240.4 provides requirements for protecting conductors against overcurrent. It specifies that conductors must be protected by overcurrent protective devices rated in accordance with the conductor's ampacity. Section 240.6 lists the standard ampere ratings for fuses and circuit breakers. Proper overcurrent protection is essential for preventing electrical fires and protecting equipment from damage. The NEC also has provisions for GFCI protection in certain locations. GFCI stands for Ground Fault Circuit Interrupter. It is a safety device that is designed to protect people from electrical shock. GFCIs monitor the current flowing in a circuit and quickly interrupt the power if a ground fault is detected. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. NEC Article 210.8 provides requirements for GFCI protection in dwelling units. It requires GFCI protection for receptacles in bathrooms, kitchens, garages, and outdoor locations. NEC Article 517 provides requirements for GFCI protection in healthcare facilities. It requires GFCI protection for receptacles in patient care areas. GFCI protection is essential for preventing electrical shock in areas where people are likely to come into contact with water or other conductive materials. One important table in the NEC is Table 310.15b16, which provides the allowable ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air, based on ambient temperature. This table is used to determine the appropriate size conductors for various electrical circuits based on the amount of current they are expected to carry. For example, a 12 American wire gauge copper conductor with a 75 degrees Celsius insulation rating has an ampacity of 25 amps when installed in free air. A 14 American wire gauge copper conductor with a 75 degrees Celsius insulation rating has an ampacity of 20 amps when installed in free air. This table is essential for ensuring that conductors are not overloaded, which can lead to overheating and fire hazards. The NEC also addresses the requirements for electrical equipment. Electrical equipment must be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or Intertech. This ensures that the equipment has been tested and meets safety standards. NEC Article 110 provides general requirements for electrical equipment. It covers topics such as equipment identification, working space around equipment, and protection of equipment from physical damage. Section 110.3 provides requirements for the examination, installation, and use of electrical equipment. It states that equipment must be installed and used in accordance with the manufacturer's instructions. Section 110.16 requires that electrical equipment be marked with its voltage, current, and other relevant ratings. Proper installation and maintenance of electrical equipment are essential for electrical safety. When working with electrical systems, it is important to use appropriate personal protective equipment. This includes items such as safety glasses, rubber gloves, and insulated tools. Safety glasses protect the eyes from flying debris, rubber gloves protect the hands from electrical shock, and insulated tools prevent current from flowing through the body. The Occupational Safety and Health Administration, or OSHA, provides requirements for personal protective equipment in its regulations. OSHA Regulation 29 Code of Federal Regulations 1910.132 requires that employers provide personal protective equipment to employees who are exposed to electrical hazards. OSHA Regulation 29 Code of Federal Regulations 1910.335 provides requirements for safe work practices for electrical workers. Following safe work practices and using appropriate personal protective equipment are essential for preventing electrical injuries. In addition to the NEC, there are other codes and standards that may apply to electrical installations. These include local building codes, fire codes, and energy codes. Local building codes may have additional requirements for electrical installations, such as requirements for the type of wiring methods that are permitted. Fire codes may have requirements for fire alarm systems and emergency lighting systems. Energy codes may have requirements for energy-efficient lighting and HVAC systems. It is important to be familiar with all of the codes and standards that apply to a particular electrical installation. Understanding these codes and standards and implementing the discussed solutions will improve electrical system reliability, minimize the risk of ballast failure, and promote safety. If you are not familiar with electrical work, consult a qualified electrician.